Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over lattice energy. And so to talk about lattice energy, I want to use an example of a reaction. So you would recognize this reaction as the formation of sodium chloride solid from its elements in their standard states. And so this is your formation equation, the equation of the formation of 1 mole of your product. And so by definition, the delta H, the standard delta H formation for this is related to this equation. So it has to be from the elements in their standard states, so solid sodium and gaseous chlorine, and you have 1/2 of the gaseous chlorine to make exactly 1 mole of your product. And so that gives you the standard enthalpy of formation. And for this reaction, we're forming a solid salt from gases, from its elements. And you'll notice that this is a highly exothermic reaction. So it's negative 411 kilojoules per mole. And so you might be asking yourself, well, why is it so negative? Well, so your first thought might be that, well, you're transferring an electron. So it takes energy to transfer electrons from the metal to the non-metal. And so the overall result of those transfers of electrons to make the salt is in here. So overall, negative 411 kilojoules per mole. But if you look at the actual amount here, so for sodium atom to your first ionization energy to take an electron away from your neutral atom is a positive 496 kilojoules per mole. So it takes energy to take away the electron from sodium. And then you have the electron affinity, which is the energy released when you add an electron to chlorine. And the electron affinity for chlorine is negative 349. So if you're doing electron transfer, you add these together and the overall result is positive 147 kilojoules per mole. So if you were looking only at electron transfer from sodium to chlorine, you would actually be absorbing energy. So this would take overall a positive amount of energy. So the transfer of electrons can't be the whole story with regard to forming the salt. And so why is there a difference between this and the standard enthalpy of formation? The reason is the lattice energy. So the lattice energy is the energy that's associated with the formation of a crystalline lattice structure. So remember, you have these positive and negative charges, and they want to be oriented in such a way that is going to be the least amount of potential energy, right? So you can't just throw them all together in some way. They're going to arrange themselves in a structure that's going to give them the lowest possible energy. And so remember Coulomb's law, right? So if you have two ions, you bring them closer together, that's going to lower the potential energy. But you've got all these negative ions, you've got all these positive ions. They're going to want to arrange themselves so they have the best structure that's going to give them the lowest possible energy. And that's going to give them a lattice structure and an arrangement of alternating negative and positive ions. And that releases energy. That lowers the energy of the substance, and when it lowers the potential energy of the whole substance, that energy is released. And so that added negative energy results in a negative 411 kilojoules per mole. So when you go from here to here, it has to do with the formation of that lattice structure for this particular salt. And all different salts have different lattice energy structures because they have different structures. Okay, so I hope that is clear. The only way that you can calculate, there's no easy way to calculate lattice structure, but one of the best straightforward ways to calculate lattice structure is called the Born-Haber process. And I will discuss the Born-Haber process in another video. Thanks for joining me. If you like this video, share this video, hit the subscription button down here, hit the notification bell if you want to hear more videos, and make a comment in the comment section. Thanks for joining me, and I'll see you next time.